tell you about the Big Bang and the way that we have observed it, will observe it some more. And then, as they say, let me show you my first view graph, but I have to do that. So I'm going to show you my charts about the Webb telescope. And where did they go? So they were here a minute ago. There we go. So what I think I'm showing you here is opening the infrared treasure chest with the James Webb Space Telescope. There is our powerful telescope that looks like a big golden hexagon against the background stars. It is a telescope with a 6.5-meter mirror, bigger than anything we've ever had in space before, and it is supposed to go up in just over 3 weeks on December 22. So I'll tell you the story of what it's supposed to do, why we're doing it, how you can use it, and then ideally we have some time for conversation at the end of all of this. You can see on my chart that I've listed that it's a joint project of 3 space agencies, NASA with the European and Canadian space agencies, and that there is a huge number of people that it has already taken to build this observatory, over 10,000 of us. So coming soon. So I'd like to start, though, before we started all of that, with what's this sort of summary of the expanding universe story, and how is it possible that I'm here? So we know the universe is expanding, that it was smooth and hot when it was young, that it is unstable. And this is not something everybody appreciates. And ideally, we would be able to explain how come we have complex structures when it's not so obvious how that works. But it's because gravity pulls things together and liberates gravitational potential energy and turns it into kinetic energy. So the universe is self-heating. Not something everybody appreciates, but we in astronomy talk about negative specific heat for gravitational systems, and it's the reason that we're here. If there were none, then the universe just would have kept on expanding and cooling off, and then it would have been boring. So it's very big, very old, possibly infinite, probably infinite, although you can't prove that. And so even rare possibilities as we think we are here. We have learned about stored DNA and language, and one way of describing the DNA that we have is it's the computer code that runs every cell. Another way of describing it is that computer code was written by random programmers over billions of years, and it's spaghetti code, and you can't possibly figure out what it does with any depth anytime soon. So if somebody said, write a random computer code and see if it works better than the one you already have, that's what nature did. So pretty strange and wonderful, and we are here because of all of that. We are also beginning to learn about the feedback loops that keep everything more or less stable while we're alive. We biologists call it homeostasis, which means your cells keep their identity even while they replace the atoms, and I keep my identity. So I still look more or less the way that I did when I was much younger. So interesting thing to try to appreciate that. And I think it's one of the reasons that astronomy is so exciting to people, that we can work on this story of how did we get here. So we have in physics the 4 forces plus the quantum mechanics, the thermodynamics that describe all of this. And if, as I said earlier, if gravity were not an attractive force, there would have never been the instabilities that brought us into our existence. But the quantum mechanics seems to be the essential feature, and still learning how to utilize its many features. But basically, quantum mechanics tells us the shape of all the combinations of the atoms with one another. So that tells us what building blocks does nature have to play with as it experiments with those genetic codes. We do know how to calculate equilibrium thermodynamics quite well. And so for instance, when ice forms and order appears in the ice, it's at the expense of increasing the disorder of other parts of the universe as the heat of crystallization comes out. Anyway, that's pretty well understood. What's not understood is the last line here, the non-equilibrium thermodynamics. And we're just beginning to learn practical ways to describe it and calculate it as compared to just looking to see what happens. So very, very interesting. Anyway, we're here basically because nature has a way of finding spontaneous heat engines that increase the flow of entropy and build up complexity. So anyway, short story of an amazing mystery of our biological existence. So in astronomy, we've been working on this instability question for a long time. When it was understood that gas clouds might collapse, it was not too hard to figure that out. So that's been known since 1902. Other things that are unstable are much harder to figure out. You want to know, is the solar system stable? Answer is, well, maybe. That's harder. Even though you say, well, aren't the laws of 1 over r squared pretty well understood? Well, yeah, but long term, it's a chaotic system. So I want to put up just a little bit about cosmology because I got famous for working on it. This is Edwin Hubble's chart from 1929. I put up the chart partly to say it's almost a century since we understood that the universe is expanding, but also to emphasize that Georges Lemaitre told us this would happen. And before it was actually recognized with this graph. Georges Lemaitre had almost as much information as Hubble had about the expanding universe, but he didn't yet have the proof that distant galaxies were made of stars. And Hubble got us that with the Cepheid variables. Hubble also got us this graph by plotting out the points, and it was, as you probably have heard many times, incorrect because the Cepheid variables that he was studying were not the same kind as the ones, the Cepheid variables in the Andromeda were not the same kind as the local ones. So distance scale was off. Took us a while to find that out. So anyway, short summary of cosmology there. Here is the thing that got me into some degree of fame. This was the Cosmic Background Explorer satellite. It was a follow-on to my failed thesis project at University of California in Berkeley. When I got there, the cosmic background radiation had just been discovered. A suitable graduate student thesis was to go try to measure it from the ground. That worked, but it wasn't interesting. Then my thesis advisor drew a balloon payload to go measure the spectrum. And well, that was a hard project. It's like a satellite on a string. And it failed to function after the first flight. So I got to write a thesis about a failed project, mostly. I thought, well, that's too hard. I'm never going to work on that again. And I got a job at NASA in New York City to work on radio astronomy. But as it happened, 6 months after I got there, NASA said, we want proposals for new satellite missions. I said, boss, my thesis project failed. We should try it in outer space. So this was the result. After lots of changes, in particular having to redesign the mission twice. First, we designed it to go up on a Delta rocket. Then NASA said, we're not using those anymore, go on a shuttle. Then the space shuttle blew up and we had to redesign to go back on the Delta rocket. Anyway, because real engineers worked on this project, it worked when it was launched, and we right away got good answers. Anyway, it was followed on by a WMAP mission, Wilkinson Microwave Anisotropy Probe from NASA, and a European Planck mission. And the upshot of that was, well, we got the right answer with the COBE satellite, and I got to go to Stockholm and get a prize. But the main point was that the standard picture of the universe is now confirmed. There were alternative pictures that we had before, say a cold Big Bang or a steady state universe with refilling the mass density with some new field. Anyway, here's now the standard picture. There was some kind of quantum field in the early universe that produced all the particles after its own instability, leading to something very hot and very compressed. It was presumed to be infinite. We can't prove that because there's just no measurement you could imagine, but at least very large. We think we're at the center, but there's no reason to think there is a center. So it's just expanding into itself. So I put this here because this is a story everybody knows in physics, but we still talk about it wrong to the public because people call it an explosion, just like a firecracker. And it's not. It is an infinite universe expanding into itself. It has no center. It has no edge. It does not even have a moment of creation the way that people talk about it, because that would mean that you had time before the expansion began, and there's no way to talk about that yet. As far as we have in physics, we only have process equations that say something turns into something else. We never have something that says vacuum turns into this. In fact, anyway, that's a weird thing. We have a story about a vacuum with a quantum field in it, but we don't have a story about an empty vacuum turning into the expanding universe. So we have told the public some very confusing tales, and that's one of the reasons that they don't believe us. But anyway, you all have a chance to make that better. So how are we going to know if this is a true story? Well, of course, we take lots of pictures. We took pictures with the Hubble Space Telescope, and we said everything seems to sort of fit mostly. But then after we got the pictures with the Hubble telescope, people said, well, that's great. We want another telescope. Please build us one that's even more powerful that can see infrared light. And so that happened starting in, for me at any rate, in the fall of '95. After they've gotten the Hubble repaired, and it was taking beautiful pictures, getting the Hubble Deep Field, astronomers looked and they said, oh, that's great, but you can't see the first galaxies growing. And by the way, since then, we also just came to agreement that there's a cosmic dark energy causing an expansion to accelerate. And then it's pretty darn clear there's dark matter everywhere. So this is what we ended up building. It is a telescope with a 6.5 meter mirror made out of 18 gold-plated beryllium hexagons. It has 4 instruments that come from Europe and Canada, and there they are listed. We'll show you more. Our big contractor is called Northrop Grumman Space Systems, and their headquarters for this is in Redondo Beach, California, near Los Angeles Airport. But we are operating the observatory from the Space Telescope Science Institute in Baltimore, and the lead part of NASA that I work at is at Goddard Space Flight Center in Greenbelt, Maryland. So we can get on the I-95 and drive up to your place, or get on the Amtrak and ride up to your place. It's not that far away. At any rate, the thing that makes this different is not only that it's big, but also it's cold. It is cooled down to about 40 Kelvin. And it will be going up on its European rocket in December 22, according to plan. So I'll show you more about what it's supposed to do, and then a little bit about maybe how you all may be able to participate in it. It has 4 main themes that were used to derive the scientific requirements. Okay, so now you say you want to build us a telescope. Well, what are the instruments that go with it? So there's the Big Bang story on the upper left, and it's a wonderful graph, but it still tells you the wrong story because it looks like an explosion, but it isn't. We just don't have a good 4-dimensional eyes. At any rate, we are looking to see what happened between the cooling down phase, which gave us the cosmic microwave background radiation and a neutral plasma, and what then enabled that to turn back into stars and galaxies. So we're looking for the first ones of those. We are going to look for how do the galaxies grow, which seem to be, according to simulations, that little bits form very early and gravity pulls them together. So we have colliding mini galaxies, and they grow bigger and bigger by collisions. Close to home, we will be looking into places like this beautiful nebula, the Eagle Nebula, and we'll be looking for the stars being born inside. The lower right-hand corner shows you a beautiful picture, but the beauty is actually not in the beauty. It's in the little white dot at the top right, because that is a direct image of a planet around another star, and all that beautiful orange and blue is actually stray light from the star that we couldn't get rid of. But we were able in that image to get the picture of the star, and we'll be certainly trying that with the Webb. So how does the telescope work? Well, here is the diagram of the great mirror. It's an almost parabolic primary mirror, has a little hyperbolic secondary mirror, and the two of them send a beam into the instrument package. If that was all you had, you would call it a Cassegrain telescope. But we put a third mirror in there to improve the image quality and correct the optical aberrations. And this makes it possible to get diffraction limited imaging, which is to say it's almost as good as it should be if it were perfect, at a wavelength of 2 microns. And the story here also explains to you that we needed to make these mirrors correct when they're low temperature. Since they will be around 40 Kelvin in space, we can't polish them then when they're cold. We have to build them at room temperature, measure them, cool them down, measure them again, warm them up, polish them some more, cool them down the next time, and hope that it's correct. We did learn how to do that. So a very long and difficult process, but we now are the masters of fabricating beryllium into almost perfect mirrors, very thin, about 2 millimeters thick. That's how it's possible to lift this gigantic telescope into space on a rocket, that the mirrors are very thin. So we have altogether 4 instruments on board: a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and finally the fine guidance sensor with a near-infrared imaging slitless spectrometer. So these cover the entire wavelength range from 0.6 microns, which is, you could see with your eyes as a red laser wavelength, all the way out to almost 29 microns, which is important because it includes, among other things, the line of rotating molecular hydrogen at 28 microns. So the cameras are used for the best pictures we can get. The near-infrared camera is used for focusing the telescope after launch. 3 of the instruments have coronagraphs, which we use to block starlight in order to be able to see faint planets or whatever hanging out near them. One of the most remarkable stories here is the near-infrared spectrograph, which has the capability of multi-object spectroscopy, and I'll show you briefly how that happens later. I've got diagrams of the 4 instruments, optical diagrams. This is the near-infrared camera, and this is the only one that uses lenses for focusing. It's an interesting, tricky thing, because how do you know the lenses can work in space? What if cosmic rays make them flash? So we had to test that, but after we decided it was okay. This was a very nice compact design. And we have 2 mirror image modules for redundancy, just to make sure that if something bad happens, which it often does, that we will keep on going. So has a smallest pixels of 32 milliarc seconds. So pretty good, but you can always wish for better for the next generation. Here is the near-infrared spectrometer. This one is made completely differently. It's all reflective optics. The reflective optics are made of silicon carbide, and so is this physical structure. Why would you do that? Well, silicon carbide is very uniform, very stiff, very rigid, and very uniform, which means that when it cools down, it doesn't warp. So they were able to build up this structure with European technology in a way that we wouldn't have chosen here in the US. We would have tried beryllium, which has got its own troubles. The upper right hand sketch there shows you how we take a piece of sky, image it on a micro shutter array, and then we let open the little shutters to let the light in from the specified pieces of sky, the galaxies that we like. And then we send it into a spectrometer to get a spectrum of each of those 100 pieces. The mid-infrared instrument is a completely different one again. This one needs to operate cold at about 7 degrees Kelvin, cooled down by a refrigerator using gaseous helium flowing through tubes and expanding. An example of its design features is, you see in the upper left here, that it stands on 6 legs. And one of the reasons that all of the instruments stand on 6 legs is to deal with differential contraction. between the instrument structure and the thing that it's mounted to when we put it in space and it cools down. And finally, the fourth one, the Canadian one, the fine guidance sensor with this slitless spectrometer, is used for a different kind of search for early galaxies, especially looking for galaxies that are bright emitters of Lyman alpha. So lots of different ways to use this equipment. So how sensitive is it? If you were a square centimeter gray object, that is to say a bumblebee, at the distance of the moon from the telescope, we would be able to see you because that's about a few nanojanskis brightness. Very, very, anyway, it's totally astonishing to me that we could do that. Bright objects are tricky for us, but we do have ways, and we can look at everything from Mars on outwards in the solar system, and we can even track them, which is tricky, but it's possible. So if the next interstellar comet comes zooming through, we will be able to look at it. So how sensitive is it? Well, these are graphs for astronomers to see that the bottom of the chart is better. The left-hand chart is the comparison of the Webb telescope with the Hubble and other telescopes. You see Webb telescope is orders of magnitude below everybody else in sensitivity from wavelength of about 1.5 microns on out to longer wavelengths. So that's where its greatest strength is. On the right-hand side, it's also the best at spectroscopy. So even though you can do spectroscopy from the ground with big telescope like the Keck or the Gemini, it's awfully bright down here. And so it's hard to figure out exactly how we're going to follow up all of the Webb telescope observations with ground-based telescopes. So we will not be trying to do the same thing. We'll be doing different things. So what are we going to look at? Well, we have three classes of observations that we're doing. The first class is called guaranteed time observations, and those are 4,000 hours of time allocated to the scientists who helped build the observatory or developed exactly what their interdisciplinary science case is. So they got first dibs on what they were going to look at. Then we had a competition to choose early release science programs. And the definition of that was they had to deliver the data to the public immediately. And they cover practically every kind of science that we are going to be doing in general. But these are going to be some of the most exciting examples, and they'll come out for you to use and see as soon as the data are taken. Finally, there are the general observers or guest observers, and they get about 6,000 hours. So by the way, this totals up to slightly more than a year, but anybody could apply for that. And the proposals are reviewed in a dual anonymous process, which means that you write the proposal so we don't know who you are. And we don't find out until we've already decided whether the proposals are the best or not. Then, of course, we have to work out the details. The result of that was what we now think is a pretty fair allocation of time to people. And not only that, about 9% of the proposals were granted to teams that were led by graduate students. So there is hope for all of us young people and people who are still beginners in one way or another. If you've done a good work, you don't have to pretend to be old to win. So this is a tally of where do the people come from and what do they want to observe. So you see it covers everything. Exoplanets gets a quarter of the time, or at least a quarter of the proposals, I should say. So practically everything is covered that you could observe with the Webb telescope. Somebody proposed to do that. So if you want to follow along and see how we're doing, participate in these things. Of course, we have YouTube, we have all the social media set up, so you can follow along with what we're doing and participate in various different ways. If you, for instance, if you want to plan for proposing next time, you'll want to check out all of our instructions about how to propose, how to calculate the observing time that it takes. There is an astronomer's proposal tool that you can download and put on your computer that will help you calculate the exposure time, for instance, that it takes to observe your favorite object. So now we want to show you some examples of what we're likely to look at and what hoping to see. So this is a little piece of the Hubble ultra-deep field, and there's just one star in this image that you can see with a little spike sticking out of it. The rest of the things are galaxies, and what the Hubble observers told us was, this is great, but we cannot see far enough back in time with the Hubble. It does not show long enough wavelengths to see the most distant galaxies. It's also not big enough to be sensitive. Even if it were cold, it wasn't big enough. So please build us a bigger telescope that can pick up the infrared. So what we expect to see when we extend this into the longer wavelength infrared is some even redder dots, infrared dots, very small. Those will be the primordial galaxies, whatever they were. And then we would have to work on them so we can understand if they are actually primordial galaxies or they're just some little red star nearby masquerading and trying to fool us. Not that that's intentional, but at any rate, that's clearly one of the hottest topics for us. We will be looking to see if this story is true. It is predicted that the way that the first galaxies would form would be very rare, unusual fluctuations at very high redshift would begin to collapse, and they would enable themselves to cool off and let out the heat of collapse by radiating it out with the hydrogen-2 molecules. And that then describes the formation of the probable first objects. If this is true, then the picture on the right-hand side should happen. The first stars might happen at a redshift of 30, and then they will immediately start to burn holes in the surrounding medium with ultraviolet light coming out. And then when they blow up, it's going to be all very polluted and very different. So it's a very interesting story to try to unravel about these very first objects, but they would have been very different from the ones we have today. We will be looking for those galaxies, and this is an illustration of our micro shutter array in the near-infrared spectrograph. We lay out the array across an image of galaxies, and we say, well, choose the ones that you care about and let those into the spectrometer and keep away all the light from other objects that would interfere with getting a good spectrum. So we can get about 100 sources at a time. And this is intended to be the diagnostic tool that tells you what's in an object, what is its redshift, how fast is it moving internally, what is its temperature. And this is why an astronomer will say that a spectrum is worth 1,000 pictures and a picture is worth 1,000 words. So these are going to be very valuable images. And we have seen from our proposals that majority of time for the Webb telescope is being used for spectroscopy. We'll certainly be looking into the dust clouds. We know this is a place where stars are being born. And the dust enables the clouds to collapse because it allows them to cool off. When they cool off, they don't have the pressure to keep them from collapsing. So that's why they form inside these dusty clouds, but also why you can't see them. The dust is very different in these two pictures. The left-hand picture is the visible picture taken with Hubble. The right-hand picture is the near-infrared picture taken with Hubble, and you can see there's already a big difference. That the dust is much more transparent, and you can see the distant stars right through it, but you still cannot see directly into the cores where stars are being born now. So the longer wavelengths that the Webb telescope can show us will be the diagnostics for those star-forming cores way down inside of there. We've got an illustration showing you the animation of showing the change of the appearance as we go from the visible band to the infrared, even with Hubble. Very different appearance. There's the optical again. So we'll be looking at the solar system. Actually, everything from Mars on out is accessible. I'm just showing you two examples that I think are really interesting because they have the possibilities of life one way or another. Europa, a satellite of Jupiter discovered by Galileo himself, was photographed by the NASA mission named Galileo a long time ago. We see these that it's covered with ice, and we know from the mission that the ice covers an ocean. It's kept warm by the tides as it moves around Jupiter. But more recently, we've seen that water comes spitting out from the cracks between the ice blocks. So NASA is sending a mission out there called Europa Clipper, which will fly through those plumes of water and see if they have anything else in them, such as organic molecules. The picture on the right is a geological map of Titan, satellite of Saturn, which is big enough to have a thick atmosphere, and it's thick enough to support a helicopter. So we are sending a mission out there to do that. So you see the geological map includes lakes, plains, craters, all kinds of things. So there's rain of liquid hydrocarbons. And this is a place where nature is clearly doing an experiment. If it's logically possible for life to have another form, which is not based on liquid water, but maybe based on liquid hydrocarbons, well, this is a place to look. There's also a possibility here that there's a liquid water ocean under the ice, which is under these hydrocarbons. That's harder to figure out. We will be looking at exoplanets. The technique you probably all know about is transit spectroscopy. If a little bit of planet goes in front of its star, and it'll block some starlight, but an even smaller amount of starlight will be passing through the planetary atmosphere on its way to the telescope. And we're talking now parts per million being blocked even for these favorable cases. So we're showing here a planet about the size of Earth going in front of a star about the size of Jupiter. So Earth is about 1/10 the size of Jupiter, so that's a 1% effect. So it's not so hard to study it as it would be for others. Anyway, we've chosen a plan. We have a long list of transit events that we know when they're going to happen. So there are 26 of them that are sort of Earth-like size. And so we don't know if they are Earth-like in any other way, but we will be finding out if they have atmospheres. And if we're fortunate well, anyway, we will certainly be looking for signs of molecules in these atmospheres, and they could very well be there. Although it's also thought that these little stars, the M stars, are so active that possibly their stellar flares will have torn away the atmospheres of these little planets, and they'll just be bare rocks. So that's a big question that we can answer probably fairly quickly after we get a shot at this. So what are we going to do? I think I told you we have the early release science program. The data will come out right away. I think I should have taken this chart out because I already told you this. Anyway, that's the place to be looking when we have data to tell you about in this next year of science. A few words about how we prepared the observatory to fly. This is what it has to go through on its way to the launch site. We built it up in the clean room at Goddard Space Flight Center, and I got my picture taken with the telescope. We put it on a shaker at Goddard and tried to see if it would break. It made a buzzing noise, but did not break. We finished packing it up into a special shipping container, sent it around the highway to the Air Force Base, and put it in a C-5C aircraft, and it flew down to Houston, Texas. We have a giant vacuum tank in Houston, which was used by the Apollo astronauts to practice walking down the ladder onto the surface of the moon. But we had to improve it to make it colder so that it would test the Webb telescope as it will be in space. It worked. We put it back in the airplane, sent it off to California, where it was attached to the rest of the observatory. And there you see a picture of the rest of the observatory. We tested it to see that it would fold and unfold properly. We shook it again out there, and then we put it on the ship and sent it through the Panama Canal and loaded it in Kourou, French Guiana. And we have taken it over to the launch facility. So it is currently unpacked, and it is beginning to be mated to the top of the rocket. So far, we're doing all right. We did have an unfortunate incident. It got bumped by the clamp that was supposed to attach it, but we tested, and there seems to be no problem, for which I am extremely grateful. So in about 3.5 weeks, we will push the button. Somebody will push the button. The rocket will go up into space, and it will go directly to the Lagrange Point L2 area of the Earth and unfold. So that is our trip coming. It will take us about 2 weeks to unfold it in space, and we will do it very carefully, one step at a time, and we will check after every step that the correct thing happened. And if not, we have another way in every case to do something about it. Here's where we're going. We are orbiting the Lagrange Point L2, which should perhaps be named the Euler Point, but at any rate, it was discovered in 1750. It's a place where the combined gravity of Sun and Earth will pull the observatory around the Sun with us every year. So we can hover near there. We don't actually go to the point itself because it's in the shadow of the Earth, and we need sunshine. It's also a little harder to get there. So we will orbit around it in a loop. So we have lots and lots of ways for you to follow on the project there. Websites are the ones I know how to use, but everybody else seems to use social media, so they're out there. By the way, you can also write to me. I will put my email in the chat room at the end, so you can write to me directly. Before I close, I want to show you that this is space projects are not the only ones that I'm interested in. You all know that we are building 3 giant telescopes from 24 to 39 meters in size. And one of these days, they'll all be up and running if we're lucky. The European one is the farthest along, and they've already started building it at the mountain. And what excites me about it is not so much that they're big, but that we are going to be able to do adaptive optics with them. Adaptive optics as a way to compensate for the turbulence of the Earth's atmosphere. And I've been working on an idea to make that work better. The way we do it currently is we send up laser beams from the ground. We make the upper atmosphere fluoresce because there's some loose sodium atoms up there, and they will do it if you hit them with the right wavelength. So they glow way up there, and you can use that as a kind of artificial star, but it's not quite good enough for the visible wavelength range that I think is so important. So here's our idea. Fly a laser beacon on a satellite and shine it down on the telescope from the right orbit. And the right orbit means put it in front of the target that you're interested in for a little while. It doesn't have to be very long, but you can get this to work. So I think this is a pretty cool thing. And if we're lucky, people will say, yes, build it. Right now, we have only completed a technical study. And if we're very lucky, in the long term, we have another way to observe exoplanets. Now, this thing I'm showing you here is not constructible today. It's called a Starshade, and this one is 100 meters across, which is bigger than my whole lot that I have my house on. So it's hard to imagine how to build it, but it's, I would say, not logically impossible. If you could do that, it would cast a shadow of the star, the host star of an exoplanet, onto a telescope on the ground, and you could get that picture that I have on the right in a minute. So Earth, Venus, and Mars are all shining right there and very, very clearly separated from the glare around the star. So why not? I don't think we're going to get to do this real soon, because this is too hard, but it's been very much fun to work on it. And so I'm going to stop now and, oh, maybe not. One more thing to show you. If you could do it, you would be able to tell that Earth out there was alive because you would see oxygen and water in its atmosphere. And you would see that the other planets in this picture are not alive because they don't have that. Anyway, now I'll conclude and be happy to have questions from you all. So thanks for coming, and please have questions.
All right, great. Thank you so much. I think I speak for all of us when we say what a wonderful lecture that was. How about we all unmute and give Professor Mather a giant round of applause for such a great lecture.
Thank you. Thank you.
All right. So now we're going to hop into a Q&A, and I'm going to hand it off to Maddie to explain how this is going to work so it doesn't get too crazy.
Yes, of course. Thank you so much, Dawson. So I will be monitoring any questions that you may having. So all you have to do is put the question in the chat box, or you can message me directly, whichever you feel more comfortable doing. And then I will read it out loud, and that's how we'll go about it. So definitely ask questions, and excited to get started.
Oh, also, faculty, we're sure if you have questions you would like to ask yourself, that's great. But if you would just put in the chat that you have a question, and then Maddie can get around to each of you. And just be aware that if it starts to run over, we might jump back in and move things along just to make sure everybody gets a chance to ask their questions.
Okay, so our first question is from Jack. Thank you so much, Jack. He asks, why is the Lagrange point better than the geosynchronous orbit?
So, for the telescope,
Yes, for the telescope. Sorry.
Yeah, so the Lagrange point is the one spot in the solar system where you can put up your umbrella on one side, and it'll protect the telescope from the sun, the Earth, and the moon all at once. So if you go out any farther, you will escape from the Earth and go zooming around the sun by yourself, and that's harder to work with. If you go a little closer in, you are in orbit around the Earth, and you cannot protect yourself all the time from all of the heat of all of them. So it's the unique spot.
And then another question that we got is from Sana. I'm sorry if I pronounced your name wrong, but their question is, how do you go about unfolding the telescope in space?
Oh my goodness. Well, I didn't show you the deployment video because I wanted to save time, but it is all done by remote control. There's nobody out there to help it along. The sequence goes more or less like this. Unfold the solar panels, make sure that the battery is never empty. Unfold the transmitter and receiver antenna so you can have high rate data. Then unfold the structure that holds this sunshade in place. Then separate the telescope from the warm spacecraft bus. Then start unfolding the sunshade itself, stretching it out. Then separate the 5 layers of the sunshade. And finally, unfold the telescope itself. Then it goes from being all wrapped up to being unfolded and looking like the picture I showed you. At the very end, we have to say, let the mirror segments loose because they're all lapped down during launch, and we have to move them ever so little to get them in focus. So it's a very long process, but as I say, everything about it has a backup.
Okay, great. So the next question is by, Raghav, and he asks, can you say a few words on how this will be used in the era of the multi-messenger astronomy? And then the second part of the question is it possible to move it based on info from LIGO, LIGO-ET.AL? Sorry if I'm saying this wrong.
Yeah, sure. Thanks. Yes, if somebody sees something and they say, well, there is an event occurred. We say we have a message. Then basically everybody in the world that has a telescope says, can I look at that thing if it's exciting? So when the LIGO people revealed that there was a location where there might have been a neutron star merger, everybody that could looked over there. And so we ended up with 4,000 co-authors on all the papers resulting from that. So the answer is yes, but Webb telescope is not so very quick. It takes us about 2 days after you have your idea. You call up the director and say, please point at my favorite target. And it takes us about 2 days to decide how to do that and send a command. So yes, we want to participate, but we depend on basically the old way of a phone call.
Okay.
So the answer is yes, if LIGO tells us something, we can follow it up, which is not so quick.
Okay, great. Thank you so much.
Mhm.
Our next question is from Dawson. Dawson asks, how did you come into your particular niche within physics? And then the second part of the question is, what advice would you give to students who will soon be discovering their own specialties?
Oh my goodness. Well, my trajectory was chaotic. It was responding to what was there at the time. So when I was in college, the cosmic microwave radiation was discovered, but I wanted to be Richard Feynman. I wanted to be a theoretical physicist because I thought quantum mechanics and relativity was the coolest thing. I got to graduate school and I was tired of studying in the library. So I went around to look at possible measurements that I might participate in. And so I found a group that was going to build an apparatus. Okay, well, my personal prejudice is building equipment is like the essence of physics. If you build something that nobody else had before, you can measure something nobody else knew before. So that's what I wanted to do. So that's how I started in the cosmic microwave radiation business. Then I told you already my story about how that didn't work so well and the proposal. Then after the cosmic background satellite was done with its operations, now what am I going to do? Well, there's an awful lot of new people in this subject. So I thought, I'm no longer that competitive with you all who are coming through school, that you know the tools that I don't know anymore. So, but then I got a call from NASA headquarters. We're going to start a study of this new telescope. Would you like to participate? So I said yes immediately. So that's how I'm in this world. And I am in it as a, what I call myself is a theoretical instrument designer. So I say, this would be cool to have this kind of equipment. How do we make it happen? So in my last 20 years or so, I have been mostly working with teams of people to get something good to happen. So it's random. And I didn't even tell you all the random events, but if there's lots of random connections.
Okay, great. So our next question is from Julia. Thank you, Julia. She asks, you mentioned how you could look at a new comet flying by. So what other unexpected astronomical occurrences have you considered?
Oh, well, you're sort of asking what are the surprises I'm hoping will turn up. So I'm thinking there are possible surprises in the very early universe where we are currently dealing with the cosmologists call the Hubble tension. We have different ways to estimate the rate of expansion of the universe, and we're getting different answers. And the answers are maybe, I don't know, 6 or 8% apart, which seems significant. So what happens there? Is nature fooling us, or has nature got something to tell us? So that's one. Maybe the galaxies did not grow the way everyone said. So we'll find out. Closer to home, I think exoplanets are likely to be surprising. suppose, for instance, that it turns out all of those little planets around M stars are completely rocky and there's no atmosphere at all. Some people will say, I told you so. Other people will say, oh, darn, I think I've got a way around that. We just should look over there. And so it's going to be interesting.
Sorry, I've been having some weird Wi-Fi issues. I'm like going in and out. Hopefully it gets better. But anyways, the next question is by Richard. Richard asks, what would you say was your most challenging moment in your career? How did you work to overcome that challenge? And what takeaways did you have from that?
Oh, golly. Well, I guess the sort of obvious thing is when my balloon payload for my thesis project didn't work. Oh, what do you do now? So I didn't actually worry about it too much because I thought my thesis advisor likes me. He'll find me something to do. So as it happened, I got a job offer from New York City from NASA. I think even right around the same time of the flight. So I don't remember if it was before or after, but I said yes right away. So I knew I had a job coming, even if my thesis project had failed to fly properly. So naturally, we all knew what had happened. And so my buddies at home, at Berkeley figured out what happened. They fixed it. They flew it again the next time. It worked that time. So that was very rewarding. But what I took from it was number one, if you do not test your equipment thoroughly, it's almost guaranteed not to work. There were 3 different ways that payload failed to function properly, and 2 of them we could have found in the lab in Berkeley. The 3rd one we never would have guessed, but it happened because of the environment in Palestine, Texas, at the balloon base, where the humidity is 100% and water gets into things where you didn't expect. So I think that was sort of the biggest lesson for me was if you do not test it, it will not work. It's not a matter of chance. So that's been in the back of my mind ever since. My opinion about whether it will work is unrelated to whether it will work.
Okay, great. So the next question is by Elijah. Elijah asks, JWST has a lot of moving parts and as you mentioned, the unfolding procedure is very complex. So how did you engineer all of that to make sure there's enough redundancy and that the precision of the instrument isn't being compromised?
Well, okay. Well, obviously it's very hard to do that. So the policy, the decision about the design is you should not have places called single point failures, where if the device does not work, there is no hope. So you try not to put them in the design. So if a thing could have a backup part, you have a backup part. That's because when you have many parts, the odds of at least one of them going wrong is not so small. So that's the number one thing. Then you say there are a few things where that isn't good enough, where you can't have a backup. So then you have to do 2 really important things. One is you get people to help you look at it and say, is that possibly wrong in some way? What bad thing could happen to that? And so we do a very formal risk analysis. We have review committees and we have a risk analysis system because human beings are terrible about risk management. We do all kinds of foolish things every day, and we don't even think about them because we get away with them. But my friends have fallen off ladders. I have one friend who died. So we're terrible about risk management. If you don't do something formal to control yourself, you will make mistakes. And of course, the 3rd thing is you have to rehearse and test everything. The Webb telescope has been folded and unfolded numerous times, and the pieces have been shaken over and over. So We have good reason to think that they will function. And at every possible time, you test them again. So for instance, how do you test yourselves? How do you test the people? So we have been rehearsing with the digital simulator of the telescope. So we send commands to the digital simulator and it behaves like the real one and sends back results as though it were in outer space doing its thing. So you get to practice everything, including how do you type and how do you meet and how do you talk and how do you do all the things that have to happen for something so big and complicated. So anyway, rehearse. That's the short version.
Okay, great. So the next question is by Tristan. Tristan asks, so far, there has been an emphasis in this discussion on how JWST might progress planetary physics and cosmology. So is there anything that you're particularly excited about in other fields such as stellar or galactic physics?
Well, sure. I am not so familiar with stellar and galactic physics questions, but it seems to me every time we get a new tool, we find something surprising. And so a good fraction of our observing time is going towards stellar and galactic astrophysics. I guess one of the obvious big questions all along is, well, how do the galaxies grow? And we have the computer simulations, which are beautiful now. And you might say, well, can I trust them? So I think here the challenge is take pictures with the Webb telescope to see if the predictions of the movies are correct. And I think one of the maybe unanswerable questions is, well, where do the black holes come from and how do they get to the middle of every galaxy? And why is there a correlation between the black hole mass and the galaxy bulge mass? So we are certainly hoping to see that correlation change or grow over time, to see the first black holes growing and the first black holes doing their thing, and see whether they are indeed they formed by galaxies or do they cause galaxies to grow. So that's a big mystery to me, and I don't know where we should end up. I don't have an expected answer on that one.
Okay, I haven't gotten any more questions, but yeah, if anyone else has any more questions, again, just message me, type in the chat. Wait a minute or two to see if anyone has those lingering questions.
Okay, well, I have a question for the people that didn't ask a question yet, which is, are you going to use the telescope? Are you going to be analyzing data? The faculty members you're working with get any access to data? Are you thinking about proposing to use it next time? So I hope somebody can be thinking about that.
All right, great. Well, since it seems like questions are stopping trickling in, why don't we all unmute and give Professor Mather one more big round of applause.
Oh, sorry, Dawson. I'm just going to quickly interject. We have one more lovely question. So I'm going to ask really fast. Thank you so much, Margaret. We love more questions. But Margaret asked, you talked about pop science. Do you have any recommended reading for physicists who are in cosmology or for family?
Oh, well, I actually am thinking the coolest science book that I read this year is by Edie Widder, Widder, and she writes about the ocean, which is an even bigger mystery than cosmology. So she's a beautiful writer of an amazing story, and you say, well, why is that so amazing? Well, it's because the ocean is a three-dimensional mystery, and stuff moves all the time, and it's luminous. So if you're an astronomer, you have already some tools to think about light. So in the ocean, creatures are always lighting up. So that's a lovely story. Anyway, it is Edie Widder.
All right, great. I see a plug by Amanda in the chat. All right, let's all unmute one final time and give Professor Mather a big round of applause.
Well, thank you all. Thank you all. It was a pleasure.
Yes, means a lot that you came out to speak to us today.
Yeah. So when we all get to travel, come visit and apply for graduate fellowships and undergraduate fellowships. NASA has things for you to think about. We have summer interns. Even if you can't travel, we have summer interns, hundreds of them. So look for them and apply.
But only for US citizens, unfortunately.
Yeah. But that's not the only choice. But anyway, yes, that's true for us, I'm afraid. Yes. I see the continued chat. Anyway, thank you very much for the invitation. It was great to talk with people. And good to see you too, Meg. So bye for now then.
Thank you so much.
What a delight.